Okay, so once Yosi gets set up, he's going to talk about observing Schrodinger cats. So, thank you, Umesh. So I'm Yosi Atia. I'll be talking about Schrödinger's cat and quantum necromancy. It's a joint work with my host in previous host in UT Austin, Scott Aaronson, and with Lenny Susskind from Stanford. And what we do here is we basically use computational complexity to tackle the measurement problem in quantum mechanics. We try to say when a macroscopic superposition effectively collapse, and there's also some take on ADS-CFT. So what is the measurement problem? So we start with the two-slit experiment, and we have a source that emit photons one by one, and the photon interferes and hits the screen here. And we get used to the fact that the photon has some quantum behavior, that it exists in two places in the same time, here. And here it becomes a classical information, and we can replicate it, we can observe it by our own eyes. And quantum mechanics tells us what is the distribution of the position of the electron, of the photon at the end, but it doesn't tell us exactly how the transition from quantum to classical happens. And this can become strange very quickly. So for example, we can put detectors in the path of the photon. If the photon goes up, then detector A clicks. If the photon goes down, detector B clicks. And from linearity of quantum mechanics, if the photon is in superposition of up and down, then the detectors becomes entangled with the state of the photon, with the path of the photon, and so they don't have a classical definite state. So you cannot say even which of the detector clicked. And it gets even stranger if we think about the experimentalist as another subsystem here. And so now the state of the experimentalist becomes entangled with the path of the photon, and there is no really end to this. So the questions are very fundamental. Aren't we governed by the same laws of the particles we're measuring? The fact that we are a macroscopical being makes us somehow feel classical about the world, and there is no exact boundary between a classical and quantum behavior. And when, if ever, can we say that a unitary evolving superposition has been measured, and the measure produced a single random outcome? And so this starts all the area of interpretations of quantum mechanics, and I will not talk about that. I will talk about something less theoretical, quantum gravity. What really initiated this research is Lenny Susskind, when he cared about different kind of macroscopic superpositions, superpositions of space-time geometries in ADS-CFT. So it's just one slide on ADS-CFT, so don't worry. If we have a geometry that contains a black hole, it can be described by one state, and the absence of a black hole can be this state. And we can also talk about superpositions of the two. And what he really wondered is whether computational complexity can give the ultimate criterion for when two branches of quantum state are separated for good. And his conjecture was that detecting coherence between two quantum states is as hard as the relative state complexity. So detecting coherence is telling, for example, the phase between the two branches, or distinguishing a superposition from a mixture, telling if a superposition collapsed or not. And relative state complexity is the number of gates that require to map one branch to the other. So what his conjecture was that if we increase the number of gates, if the distance, the relative state complexity between the two branches is very, very large, then it will take a very complicated experiment to tell if they are in superposition or not. And this will be an effective collapse. So we proved that his conjecture is basically true. So here is the most simple theorem in our paper. So given two orthogonal states, alive and dead, suppose there is a quantum circuit with T gates that distinguishes alive plus dead and alive minus dead. Then there is also a quantum circuit with approximately T gates that swaps alive and dead states. So what it means is that if someone hands you a Schrödinger cat state, in order to verify that you have a Schrödinger cat state and not just a mixture of probability half alive, probability half dead, you need the computational power to revive a dead cat, to swap an alive and dead cat. And assuming that you don't, we live in a world that this is impossible, that death is permanent, and it means that for our perspective, we can never really observe a Schrödinger cat. Or alternatively, in the Wigner friend experiment, if Wigner can watch his friend in a superposition of two states, then it means that Wigner can also swap the mental state of his friend, and his friend doesn't have, is not really a free agent. And we generalize this to imperfect distinguishing and imperfect swapping. And just want to mention that there is a previous work by Atia, Aaronson, and Berkeley that gave something similar, but with less quantified. Yeah. So really the technical quantity here is the swap complexity, and that really interests me as a future research, which is the complexity of swapping two states, and which we prove that correctly captured the hardness of coherence detection. So swap complexity is not the same as relative state complexity, and we found an exponential separation between the two. And also, interestingly, it's not even a metric. The triangle inequality is not always, doesn't always hold. For summary, in quantum gravity, like Lenny wanted, we can treat superposition over space-time as effectively decohered. We have so that we have two different set of operators in each space-time, unless it's feasible to swap one space-time with the other. This is unconditional, so no complexity theory assumptions were made. So no polynomial time experiment can observe interference between a state that is exponentially complex and a state that isn't. And assuming, and with previous result by Aaronson and Susskind, if P space is not contained in the PP/poly, then no polynomial time experiment can observe interference between an early time and extremely late time CFT states. And in foundational implication, so our results sort of formalize the folklore that interference between branches stop being detectable precisely when irreversibility sets in. And we sort of quantify what, we give some kind of way to quantify what is irreversibility by this swap complexity. And interestingly, the reversibility here is not induced by some random interaction with the environment like we're used to. Even if everything is unitary, you can get some sort of effective irreversibility, effective decoherence, just from computational complexity, just from the what the observer, the computational power of the observer, and this really depends on the power of the observer. So different observers can look at the same system. One can see a collapse, and the other can see still superposition. That's it. Thank you.
Thank you. So I have a question by Milan Setzer.
So why is distinguishing alive plus dead from alive minus dead the same thing as distinguishing, coherent state from a mixture?
So if you cannot tell the phase between them, then I guess if you try to build a density matrix from this, knowing that you cannot differentiate between them, then the sort of you lose some of the diagonal elements and you just look at the mixture. It's just an operational thing.
Okay, so it's just like a little lemma or something that those are one or just to the other. Okay.
So where does the swap gate fail to be a metric? Is it in